Okay, next example of a system of inequalities. My first inequality is going to be a quadratic one. Y is greater than or equal to x squared. And then a linear one, y is less than 4 minus x. The first one is going to have a solid boundary because of or equal to. The second one will not because there is no or equal to. Hopefully by now you recognize y equals x squared by its graph. The basic parabola passes through 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. Solid, sketch it through. In this case, I cannot use the origin. Boundary passes through it. I have to choose another point. Convenient points would be 1, 0 or 0, 1. Whichever one you choose, note it, plug it in, see if it's true or false. Let's go with 1, 0. If it 1, 0. 1, 0 is right here. Sorry. If it works, we shade outside the parabola. If it doesn't work, we shade in. 1, 0. Make a note of it so you know which one you're testing. Replace your variables. 0 with y, 1 for x. True or false. 0 is not greater than 1. That's false. So again, figure out where you are. 1, 0 is right here outside the parabola. It failed. So every point outside the parabola fails. All the points inside are going to work. Note it. Arrow there, pointing inward. When I shade, I can only shade stuff inside the parabola. But we have another boundary. Let's deal with it. This one is in slope-intercept form. We have a y-intercept of 4. The slope is negative 1. As a fraction, it'd be negative 1 over 1. So start with the y-intercept of 4. Negative 1 slope means down 1, right 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. This is a dashed boundary. Since I already know that I can only shade inside the parabola, I'm either going to shade up here or I'm going to shade in this closed region here. I have to figure out which side of this line is. Here, I can test the origin. So 0 is less than 4 minus 0. That's true. 0 is less than 4. Where was my test point? It was below the line. Shade below the line. So I have to be inside the parabola, but below the line. It has to be that region right there. All right, so now that's how we don't go about graphing an inequality and graphing a system of inequalities. And I just got disconnected again. Hold on. All right, so now linear programming. As you can see here, linear programming is a procedure used to optimize quantities such as cost, profit, minimal cost, maximum profit, things like that. You're going to have an objective function, which is going to be a function in 2 variables. And then you'll have some system of linear inequalities. We call those constraints. Those constraints are going to give us a shaded region that we call our set of feasible solutions. We then work with our objective function to maximize or minimize. And again, All right, here we are again. The fundamental theorem of linear programming says this: your optimal value is always going to exist at a vertex of your shaded region. So when we graph our shaded regions, we're going to look for all the corners, and those are going to be the points that we test to maximize or minimize whatever it is that we're maximizing or minimizing. So let me pause this once again to set up the example. All right, I can't tell if it's recording or not, so we're going to give it a shot. Here we have our example for linear programming. We have a function minimize. It's the function f with variables both x and y. There we are. There, I'm back now. Okay. Function f with variables x and y. 2x plus 3y is the function. We have 4 constraints. X plus y has to be greater than or equal to 4. 2x plus y has to be greater than or equal to 8. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. In linear programming, they'll always be or equal to. Therefore, all boundaries have to be solid because we need the corners. We need the edges. So here we go. We start with the x plus y is greater than or equal to 4. X and y intercepts pretty easy to find. If x is 0, y is 4. If y is 0, x is 4. Plot the point. 0, 4, 4, 0. And draw the boundary. If I test the origin, 0 plus 0 is not greater than or equal to 4. That means I have to shade away from the origin. X plus y greater than or equal to 4. If I test the origin, 0 plus 0 greater than 4 is false. Shade the other side. Again, just by marking it so that we know in the end that's where we're going to get our shaded region. Next one, 2x plus y is greater than or less than or equal to 8. Again, x and y intercepts pretty quick. If x is 0, y has to be 8. Plot the point 0, 8. If y is 0, x is going to have to be 4. 2 times 4 is 8. So plot the point 4, 0. And here, if we test the origin, 2 times 0 plus 0 is 0. 0 is less than 8. That's true. So for the steeper line, we have to shade toward the origin. So now we can see, hold on. All right, so our shaded region's got to be in between these lines right up here. Now we have 2 more constraints. X is greater than or equal to 0. That's the vertical line to the right. X equals a number is always a vertical line. It's the y-axis, but everything to the right. Y is greater than or equal to 0. Y equals 0 is the x-axis. So that's everything at the x-axis and up for greater than. So here we go. Basically, I have to be in the first quadrant because we have to be above the x-axis and to the right of the y-axis. And we have to be in between the 2 lines in this region here, which makes it that triangle is our shaded region. Its corners are going to give us both a maximum and a minimum. So at 4, 0, 0, 4, and 0, 8, plug them into our function, f of x, y. F of 0,